morning to everyone. I am, as the instructor name suggests here, I'm Sheikh Farooq Ali, who is going to take your course on instruct you on strength of materials, and that's going to be the course this year. Yes, as the name suggests, we are going to discuss about the strength of different structures that we make of different kind of materials. So it has various things into it, and we are going to learn about the thread of this course as a very beginning part of it. In the sense, we are going to look into the very basic parts of strength of materials, which will help you to understand the whole subject of mechanics. This is one of the words. So one of the picture here is taken from a book on strength of material. It's supposed to be experimental, that was done hundreds and hundreds of years before, how they used to do experiments on cantilever beams. The object is the subject, strength of materials, or the subject mechanics itself is very, very old. One of the oldest subjects in any kind of engineering and sciences possibly. And these mechanics have given rise to various kind of different, branches, not only in mechanics, but also in physics, in mathematics. And that's why mechanics is so important. And I'm glad that all of you are mechanical engineers and are going to take the the torch that we are bringing so long for mechanical engineering, and you're going to take it ahead in practice as well as in research, right? So that's why it's very important for you, if you are going to stay in mechanics, to learn the trade-offs in the strength of materials itself. Okay, I am Dr. Sheikh Farooq Ali. I do research and teaching in the Department of Applied Mechanics in Institute of Technology, Madras. And this is the first course that we're going to look into strength of materials. So probably this is also your first course in mechanics, dealing with more about mechanics. You have done engineering mechanics, which is also a part of mechanics, but that did not deal with the the inside picture of any structure. That tells you on the overall outside picture. There were a few parts where you have drawn BMDs and SFDs, which are internal forces, and they are the internal internal intricacies of a structural when they are loaded. But overall, you have done only rigid body mechanics, right? Here we are going to do it for non-rigid or flexible bodies. We are going to learn a little bit more details on that, and we will understand it as we go ahead. Okay, yeah. So this course is going. It's a big course, and there are 100 students in my class, and therefore it's not going to be handled so easily by me only, right? So I need a lot of TAs, which are my students, who are going to help me in dealing this course. And believe me or not, they are much more efficient in strength of material than me. They all are doing research in the current area of mechanics. I am a bit old, so I just guide them. But the understanding of mechanics for them is rich, and they have the current mechanics understanding of current mechanics. Okay. Suvanshu is a PhD student with me in our lab. Our lab is called Vibration Energy Harvesting and Controls Laboratory, where we look into the vibration part of the mechanics. And Suvanshu is working on energy harvesters currently with impact. Okay, so she is going to look into discontinuities that comes due to impact on mechanical structures, so mechanics, and discontinuities in mechanics. So he's going to work in nonlinear mechanics. There is then Mr. Dalroti, who is also a PhD student currently. He is working in multiple oscillators, connected together. So synchronization in mechanics, how synchronization helps to get various properties in mechanics. So he's going to work on that area. Srimanto is one step, more than Dalroti. So he is going to look not only into synchronization, but how controls can be used in synchronization. Okay, so that's his part of work. Gautam is working on morphing structures, so he is looking into how mechanics can be used for application of morphing structures. So that's his part. Sweta is going to lead the whole team. The team of these four is going to be led by Sweta, and Sweta works in soft mechanics, in the sense where structures are very, very flexible. So when I say soft mechanics, you can assume a snake is a soft mechanic structure, right? It can bend a lot, it can deform a lot. So these kind of structures are called soft structures. So Sweta is working on soft kind of materials which called soft mechanics. Then Rahul and Arvindan, they are also working in mechanics. So they are not going to be directly, you are not going to see them directly, but they are going to be at the background, helping Sweta understand the whole intricacies of handling a course. So they are all TAs. You can write to them anytime if you have any queries, and they'll be happy always to help. Okay. Now coming to the next part, why we learn mechanics? What is so important about mechanics? Now, if you ask me, strength of materials is a very basic course. And when I say it's a very basic course, I mean it is a prerequisite for many advanced courses that you are going to take later. Okay. Many advanced courses. Any course that you do from, from your second year one onwards till you do PhD, if you stay in mechanical engineering or in mechanics, solid mechanics, or in fluid mechanics, right? So any related to mechanical sciences, you will need this course. Okay, you will use this course left and right. So this course, strength of material, is is going to help you in finite element analysis, in structural analysis, in solid mechanics, in design and design of and optimization of structures, elements, whatever you do, and also in fatigue and fracture. These are the some of them I have mentioned. There are many more. So this is the basic course for people who do in engineering design, people who work in naval, people who work in mechanical sciences, civil engineering, aerospace, applied mechanics. Even there is a part which is going to help in physics also. So mechanics, you have learned mechanics in your physics courses in your probably class 10, 12, right? So mechanics is a very strong part of understanding how even how nature behaves. That can also be understood using mechanics. We will give a lot of examples as we go on. And nowadays people do use a lot of mechanics in biology, right? How cells behave, how human body behaves, all these are also understood in terms of mechanics, in the understanding of mechanics, right? Even nowadays, drug delivery, drug preparation are also understood in terms of mechanics. So there are people looking into various directions, right? One of the directions is the mechanics of it. So I would request all of you to please pay attention into this course, because this course is going to be a very important course, and for some of you this is going to be your bread earner, right? So pay attention. Okay, why we do mechanics for design? You can see that a cycle spoke. Okay, all right, you can see a lot of spokes in the cycle. I don't know whether you can see my red highlight thing here, highlighter. There is a highlighter, but I don't know whether you can see it. But you can see a cycle has a tire around it, and there will be a rim after that, and then there will be spokes, right? Now the point is, why don't you make the cycle completely solid? The wheel of the cycle is not completely solid. Why is that? Why do you need spokes? And how do you think the small, very small spoke with a very small diameter can withstand that whole pressure? How does it do that? All these are part of mechanics. So you need to understand the internal mechanics, why it's not buckling, right? Why it's not breaking in stress. Okay, what happens when you have no air in the tire? All these can be understood from the perspective of mechanics, and we will see towards the end of this course that whether we have really learned those things or not. How many of you can explain these phenomena using the help of mechanics that you learn? There is a picture next of an old iPhone, I think iPhone 4 or 5, very old one. How do they make these phones, break proof when they fall, right? The whole phone is glass, right? If you throw or if you fall a glass, general glass for drinking water, it will fall and break. But why doesn't an iPhone or any other phone which are made sturdy, fall and break. How is the shock when it falls? It gets a shock. How is that shock and the vibration absorbed by the reams? And it's not being the energy is not being transferred to the glasses so that it doesn't break. All these are part of mechanics, and you have to learn the intricacies of this mechanics, because these all will help you in the future products that can come, right? So when you see when you see a phone, don't assume that that phone has only been made by electronic and electrical engineers, right? There are huge contribution from mechanical engineers there also. They cannot come out with such a slim phone unless mechanical engineers help them. Okay, a mechanical engineer has to deal with the durability, the flexibility, the failure proof, all those things of that small structure from their understanding of mechanics, right? So that's where mechanics play a role, but that's not up in the front, it's in the back end, because phone is mostly looked at and used by people for other purposes, not for purpose that are related directly to mechanics, right? But even then you can understand that there are a lot of mechanics into it. Next comes a helmet, a bike helmet. You can see that bike helmet, some of the bike helmets are completely full, right? There is no holes, and some bike helmets will have holes. Okay, so when you have a hole in the bike helmet, where do you make these holes? Can you make hole everywhere, that wherever you want, or you can make it at only in certain places? What criteria will play to make sure that you make a hole and it doesn't it still serves its purpose? So a helmet is made for serve a purpose, right? It should make your head fall proof, right? So it has to absorb all the energy when you fall. When your head falls, it should absorb all the energy, and no harm should happen on your head, right, to your skull. So if I make holes, will it satisfy that? Those understanding has to come from your mechanics. Okay, and we will see how we can make sure that these understanding are clear in this course. An example, you can see a car crash. I have taken it from internet. You can see a car crash. You see a lot of red dots, right? So these are all a stress analysis picture here. So if you want to do this kind of analysis, you have to understand the mechanics that is related to it. Okay, why certain parts break, why certain parts fail or buckle or become unstable, and why certain other parts do not do that, right? So all these are part of understanding of mechanics, and you will do that as a part of this course. Here is another one, another structure, okay, that collapsed because of vibration into it. What happened? Why it happened? And you can see there is a car below it. So there was a repair that was going on, but it failed while it was under test or under repair. So all these understanding has to come to you. I'm not making it sure that you will understand everything, but you will at least have a judgment that this can happen. To understand everything, you have to take a lot more courses, right? Lot more courses after a strength of material, right? And then you can understand the complete picture. Here are a few analytical perspective. How do you analyze the structure? So you need to analyze how loads are transferred. So this, if you see this first picture of a truss, wooden truss, the load that will come on the truss will be wind load, or maybe the snow load, or maybe dead load from the top of the roof, and how that load is being transferred to the ground. Because you understand, you have learned from your engineering mechanics that we transfer all loads that comes to a structure to the ground, right? For example, like we say in electrical engineering, that all electrical currents are transferred to the earth, right? You have earth in, are all earth will balance all the current that you have. Similarly, all structural loads go to earth, right? So earth accepts all kind of loads that comes from a structure. So how do you transfer that load from one point? Let's say you have a load at the tip of the structure. How do you transfer that to all the points and then to the ground? So that's part, that's an analytical part, which we will learn in this course. How does it that? And when you transfer that load, what happens to the structure? What is the internal arrangement that goes into the structure to take care of that load? So internal deformations, the relative deformations, and the stresses and strains that come into the structures. We have to learn all those things. Similarly, you can see another structure here, a long span bridge. There are a lot of long span here, and then the flexible structures, right? For an aeroplane like this, or aeroplane like shown in the last part picture. How do you make structures flexible? How do you make aeroplanes fly like birds? So you have to make them more flexible. Which materials can make them flexible? What would be the thickness of these materials to make it flexible? When you make thick, what do you make thin and thin structures? What happened to the stresses and strains that come into? Will they fail or will they survive? All those studies starts with SOM. Here are a few more pictures from our lab itself. This is done by Agna, a bistable material, where he's doing some analysis in ANSYS, where a material plate can have two different states. One of the state is right now shown, and the other state is shown in the beginning, right? So two different states. So these are called bistable material, and he has also designed a bistable turbine blade based on his experience on the study. So we how do nonlinearity come into the structure? Will not be a part of this course, but you will definitely learn a little bit of it. A few more. These are by, I think, Rahul. How do you calculate stresses and strains? So this is a portion, a sector of a turbine blade. You might have learned what is a turbine blade. You might know they are mostly used in the engines of any kind of aero vehicles. They're used in many other places. One of the most important. This is for an aero vehicle. So one of the most important application is the engine of an aero vehicle. This is one blade, one sector of it. How do you design this blade? Right? Which part will be rigid, which part will not be rigid, where it can fail. So these red parts tell that it can fail at those locations. Okay, how do you calculate which part will fail, and how do you strengthen that part? What should be thickness along the blade? So this thickness along the blade is actually vary, right? So you can see this part of the blade, which is nearly blue, has no stress or has less stress. So we can reduce the thickness that part. But the red part, where the stresses are high, we have to increase because that has to satisfy and serve those purpose. It has to self-sustain there. Okay, so these are a few examples. We'll go into those examples as we go ahead in the course. Now let's get into the details of the course and the syllabus, because that's what probably you want to know right now. Okay, I'll stop for a minute. If you have any question, I'll be happy to answer. Okay, do you have any questions on this? Hello? Anybody has any question till now? No? Okay, then we'll go ahead and continue. All right. So where do we stand today? Any kind of design problem that is given to you, okay, you have to understand the design problem from a system perspective. And when you understand it from the system perspective, you have to learn what are the loads that are coming to the system. And when the load comes, how it behaves. Okay, so you have to calculate something internally, because I will not tell what are these, because we have to learn this as the course goes on. So there are some internal properties, right? Some internal properties of the system, which will show whether the system is behaving properly or it is not going to behave properly, whether it's going to fail or not. So this part that is within the block is the part that is going to help you to understand. This is one part which we are going to learn in this course called Strength of Materials. So we're going to learn about the forces that are coming to the structure, how that forces and moments can be transferred to the internal forces or internal moments, and how it helps you in design. That would be the primary part of this course. Right. So we'll learn what are the criteria that are necessary to check in design, right? Maybe the internal forces, maybe the internal deformations, and how to calculate those given a force and the structure. This is the course syllabus. Okay, you don't have to write anything. I'll upload this slide so that you don't have to write anything. We will have Professor Rajan and I have discussed. Somebody has its microphone open. Any question on this? No, right? All right. Okay. So what I was discussing is we will have day by day. This is a day by day schedule of the course. We will have two, objective type questions or tests in between, which will be 20 marks of each. An average of that will be taken for your final exam. And there will be assignments given to you, 10 assignments, 10 into 2, 20 marks. So 40 marks is completely from the course as you go ahead. It's called internal assessment. And there will be 60 marks on your final exam. Now, how the final exam will be conducted is not yet known to us. That will be decided by the institute. As of now, we don't know, right? So first few days will be on stresses. We will give you one tutorial on stresses, and you have to solve and submit it by a date. Then there will be a principal stresses and Mohr circle. There is no point of discussing this because I have not told you what are these, right? So please go through this. This is the general part of the course that should be followed as we go ahead. And then you can see the tutorial 4, 5, and the course will end with 46 or 47 lecture classes. Okay, we don't have, I don't think so we do have many more. So there will be 2 or 3 classes that will be left at the end, which we will use to go through the complete course again. So a revival of the full course will be done at the end of this. So the book I'm going to use is Mechanics of Materials, Hibbeler. That's the primary book for solving problems and for your own consumption, right? There are a few more books which I will follow while doing the course lectures. One is Introduction to Mechanics of Solid, Kandal, Dahl, and Sivakumar. So this is one of the good books that you can keep. And then Strength of Materials, Elements of Strength of Materials by Timosenko. So this is a book I'm going to follow when I'm going to the second part of the course. That means after quiz 2, most of the part will be taken from this book, The Strength of Materials by Timosenko. The first part of the book will definitely be from Hibbeler, as well as the most of the tutorials will be from RC Hibbeler. As per as NPTEL lecture, since this course is online, I will suggest you to go through the NPTEL lectures also if you miss some classes from my side. Although my lecture videos will be uploaded on the Google folder again, Google Drive again, and you will have the access to that. But in case you want to go through the courses, there are a lot of good courses by S.K. Bhattacharya, S.C. Sarma, and M.S. Sivakumar on NPTEL. Okay, so it's going to help you. If you want to have extra knowledge. I am not the ultimate person to talk about SOA. There are a lot more better, well-known expert in this area, and they will definitely help you to understand more. Outline of the course. If you talk about the course outline, it's going to be stress, strain, deformations under various loading for various kind of structures. This is what we are going to learn in this course. So if somebody asks what is the stress, if you're able to answer yes, strain yes, and deformation yes, then you know the course. Differentiate between different kind of materials. How do you differentiate between copper and aluminum? How do you differentiate between steel or a concrete and steel? If you can differentiate them based on some properties, concrete mechanical properties, then yes, you have done this course well. Understand and differentiate between different modes of failure, how structures have failed. Can this is something called what to do post-mortem analysis, right? So forensic study. So this is that kind of study for structures where after the failure of structure, can you tell by looking at the failure what happened to the structure, what kind of loading led to that failure? Okay, or if you want to do it before structure, then before the failure, then you have to tell me what are the what can happen given a loading on the structure, what kind of failure can happen on the structure, right? And then calculate principal stresses and strain. So stresses and strain are direction dependent. So which direction it will be more, right, and which direction it will be less is what you have to understand through this course. And then design criteria. What should be the design criteria? While doing this, you need to understand 3 things about a structure, that is called strength, stiffness, and stability. All those 3 will be part of this course, and these 3 S, we call triple S, is going to be the pillar of strength of material course. So you have to look at this course from understanding of strength of materials or structures that are made, stiffness, and stability. We'll define all these as we go ahead. But these are the 3 A's you have to understand. At the end of the course, you have to ask yourself this slide. You have to ask yourself, have you learned all the things that are there in the slide at the end of the course? Okay, prerequisite of the course, you need to know engineering mechanics quite well. Force equilibrium, support reactions are very important part of this course. Any question? No. Okay. BMD and SFD are very, very important for the second part of this course. So I would request you that you keep practicing BMD and SFD till the second part of this course, because if you don't know, or if you cannot draw a BMD SFD correctly, then you will not be able to do rest of the part that you are going to learn in this course. Okay. If your BMD and SFD are wrong, your whole solution will be wrong. So please learn that. Please practice that. Truss solution, how to calculate forces in truss. You have learned it already in your engineering mechanics. So please revise that. How to calculate internal forces in trusses, beams, and other structures. Calculus of centroid, first and second moment of area. All those things you have learned it previously. Keep them at your hand so that when we discuss it quickly and you get a grasp of it. So we will not spend time in this part of the courses as a full time and in the class. From the mathematics perspective, you need to know how to solve ordinary differential equations. I hope you have all learned ordinary differential equations and you will know how to solve them, because we are going to take at the end of this course some part where we have to calculate deformations. We need ordinary differential equations and their method to properly explain those parts. Okay, so please go through these parts. Just slight revision should be enough. You don't have to be very expert on this. Yes, of course, by the end of 4 years you have to be expert, but right now it's not necessary to be an expert on this, but a knowledge of this will help. Okay, learn everything in Google Classroom. Okay, so with that I will stop now.